Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending today's webinar, Best Practices for Implementing Adhesive Bonding Solutions Utilizing the Latest in UV LED Technologies. We're pleased to acknowledge a very large audience today with people signing in from all over the world. Please note that this webinar is being recorded, and you will be able to access both the recording and the presentation slides once they are available online, which should be within a day or two. If you have any questions during the webinar, please use the GoToWebinar question tool. We will reserve time at the end of the webinar to answer as many questions as we can. Today we are fortunate to have three very knowledgeable presenters. As Director of Product Management OmniCure at Lumen Dynamics, Mike Kay works closely with customers to design and develop both lamp and LED UV curing solutions for a variety of industrial applications. Mike's extensive industry experience in 13 years with Lumen Dynamics makes him a sought-after speaker on the topic of repeatable UV curing processes. Frank Hart is an industry veteran with over 18 years of experience. As Global Sales and Marketing Manager for PVA, he works with global OEM, EMS manufacturers and material companies to provide expertise in all aspects of the fluid application process. Frank has authored numerous papers on related topics. As Vice President of Sales for Enercon Industries, Ryan Schulke leads a team of knowledgeable surface treating application specialists. His passion for innovation and customer success is a driving force behind Enercon's plasma and flame surface treating solutions. Some of the topics that we will cover today include emerging applications for cured adhesives, how surface treatment improves adhesion and how your application determines the right technology, your options for syringe and precision valve adhesive dispensing, and tips for qualifying the best solution for your application. We'll talk about when to use UV lamp and LED curing solutions, and Mike will bust one of the myths about LED decay rate. We'll also talk about options for automating your process, and again, we'll reserve time at the end for a question and answer session. So let's get started with the topic of applications that are emerging for cured adhesives, and with that, I'm going to pass the presentation to Mike Kay of Lumen Dynamics.
Great. Thanks very much, Mark, and welcome to everybody today. I'm going to go into some of the emerging applications that we see from the UV curing aspect. So we can go to the next slide, please. Thanks very much. Now, I won't go through every application that's on here, but we've listed a number of applications across a variety of fields that we have seen growth in over the last few years. Things, for example, in medical device manufacturing, electronics manufacturing, in photonics, automotive applications are a number of the areas where we've seen growth in the UV curing application. Some of this growth has been driven by the parts that are being made. So, for example, in things like smartphones and tablets, which is an extremely fast-growing market, there's multiple UV curing applications such as the touch panel, the micro speaker, or the miniature cameras that are contained in each of these. And so we've seen lots of growth in UV curing through those. The other thing we see over the last couple of years as an emerging trend is something that we'll get into more later on in the presentation, and that's we see a transition of people who are currently using lamp-based curing technology and looking to move into LED. And we'll get into some of the reasons why, but some of those applications, things like, for example, OLED displays, where it's a growing application in itself, but within the manufacturing, it's a very heat-sensitive application. And so one of the things people are looking at with LED is using this technology as a way to minimize the heat. Other things, for example, like the fiber coatings. This is an application that has been done over the last number of years, but just now we're starting to see people, an emerging trend is to start looking at LED technology again, and in this case it's a cost savings from an energy savings point of view. And so some of these, again, we'll talk about later in the presentation on the benefits of LED and also some of the limitations, but these are the applications that we see from a curing standpoint. Frank, is there any applications that you wanted to highlight here?
Well, I think this covers most of them. I think as we've discussed, you know, we're also seeing an increasing trend on the dispensing side in miniaturization in all of these markets, frankly, as you know, applications for smaller dot and bead size, especially in the tablet, mobile phone markets. Also, the benefits of, you know, reducing work in process as a result of the immediacy of the UV curing process are attracting more customers. And you know, again, what's, you know, really right up our alley is in the conformal coating market, where again, you know, improvements in the materials and typically in the secondary cure mechanisms of the materials, you know, have really advanced their use across multiple markets as well. So we're really seeing, you know, a strong trend of moving a lot of our customers utilizing UV materials now.
All right, great. So as with that, we'll go on to the next slide and pass it on to Ryan from Enercon.
Thanks, Frank and Mike. Adhesion can be impacted by a variety of factors. I'd like to share with you a base level of knowledge to help you improve your bonding success. Each of these items listed here play a role in your success. Some on all applications, some on applications here and there. For example, some materials are inherently easier to treat than others. Difficult to treat material that we see quite often is anything in the fluoropolymer side. These tend to be very difficult to treat, although we do have some technologies which will allow that. Chemistries of both the adhesive and the part that you're treating play a role. Ultimately, we need to find a technology that helps alleviate any challenges that you face. So this is a graphic that I love. It's an easy way to think about the influencers of adhesion. Four things tend to contribute to adhesion issues. First one is surface energy, and in particular, low surface energy, of which most plastics inherently have low energy or a lower surface energy than the adhesive that you're looking to bond with. Contamination is also an issue, and that can be everything from mold release to maybe a part that's been sitting around for a number of months and is just dirty or dusty. Additives which migrate or bloom to the surface can be a surprising issue. Sometimes one of our customers will run a part and treat it and bond to it 1 week, and then a week or 2 or 3 or 4 later they run the same part, maybe the same batch, and they're having problems. And often we'll find in those cases it's blooming additives that cause their issues. The final pieces are limited bonding sites. And all of these contribute to a surface being hydrophobic or not wanting to accept an adhesive. So, low energy, lack of bonding sites, and contamination all contribute and have a negative impact on adhesion. What we see in the upper picture is a droplet of an adhesive that is failing to wet out, or it's staying cohesive with itself. This contrasts with the lower image where the adhesive wets out, lays down, and ultimately forms a strong bond with the two parts that you're looking to bond together. What we are doing by preparing the surface is lowering this cohesive force and ultimately creating a stronger bond. You have a variety of solutions to help prepare the surface for your part. You can use a liquid primer. These commonly used process that really faces a few challenges. One, it's a secondary process that you either have to apply by hand or with another piece of equipment. And then you also have the environmental concerns as well as the cost that goes along with the primer that you use. Mechanical preparations, such as skiving, maybe in the folding carton industry. This is another case where there's a wear part that you're going to run into. There's cost associated with that. There's time, and it tends to create a fairly dusty environment. Vacuum plasmas provide a solution to both of these first two items, in that you take a batch process, put your part in, and use a plasma technology to treat the entire surface. Fairly effective, however, they are fairly capital and time intensive. They tend to be batch processes, so your throughput tends to be a bit lower. Throughput is one of the areas where atmospheric plasma and flame plasma solutions tend to shine. They are inline, continuous, they can be robotic, and fairly economical. So one of the questions we get quite often is, what is plasma? And I like to tend to describe it as an ionized gas. More correctly, it's a mixture of charged ions and energetic electrons in equilibrium. So one of the barriers to surface adhesion that I mentioned earlier is a contaminated surface. This can be organic or inorganic materials on the surface, essentially low molecular weight materials. The charged ions and energized electrons present in the plasma treating process help clean and remove this contamination. Cleaning a surface is not the only thing we're doing when we plasma treat. In addition, we are creating more bonding sites by micro-etching the surface. In some applications, we take it even further by adding an inert gas into the process, which leaves a functionalized molecule on the surface designed to enhance adhesion with specific chemistries. So now I want to talk a little bit about what the different types of plasma treating systems are and how you would go about selecting one for your application. So this is a great gallery of the different types of plasmas that we'll talk about. I'll review them here quickly and then we'll go into depth a little bit more. So the column on the left you see, that is our blow and arc plasma treating solutions. The second column are what we call blow and ion plasma treating solutions. The third column is an example of variable chemistry plasma. And the final column all the way on the right are examples of our flame plasma treating technology. So blow and arc plasma is created by passing a high voltage electrical discharge between two electrodes. If you look at the picture on the top, you see the purple discharge coming out. There are two metal electrodes right beyond that, and the charge jumps back and forth between these two metal electrodes in the head. It's useful for a wide variety of applications. Generally, it treats anywhere from 2 to 3.5 inches with a single head. Multiple heads can be combined for wider treatment patterns. An important thing to remember about blow and arc is that they can only be used to treat non-conductive materials. That is, any non-metallic materials. This is important not only for the material that you're treating, but also whatever carrier you are using to move your part down the line. This tends to be best for slower speed applications, say in the neighborhood of 30 feet per minute. The secondary plasma technology is blow and ion plasma. The plasma here is generated inside the head, and the resulting ions are blown out via compressed air, and that's the yellow and purple discharges that you see in these pictures. It tends to be a very versatile treatment method in that we can treat both conductive materials and non-conductive materials. The treatment width is a bit narrower than blow and arc systems at about 1/2 inch wide. And these are particularly great for adhesive applications. They're often used to treat glue tracks in automotive headlamp applications, glue flaps, and folding carton applications. Variable chemistry plasma is very similar to blow and arc, except that we are adding an inert gas into the mix. This technology tends to be used with the materials that are difficult to treat. We are able to produce this technology in 2 formats. What you see in these pictures is about a 2-inch treat width that's used for a variety of objects. In addition, we're able to custom design a system for flat and wide objects. This could be a flexible material or something rigid like a piece of glass or a piece of plastic. The final technology that I want to share with you today is our flame plasma treating technology. Flame treating is probably the technology that most people are familiar with, as it's been around for many years. We've improved upon this technology greatly to create a safe and consistent treatment method. With flame, you're able to treat both conductive and non-conductive materials at extremely high speeds. The flame's width can vary from as small as 2 inches to over 16 with our standard products. And we will custom design products for even larger than that. The effective treatment area of the flame is also very deep, which allows you to treat objects with great deals of contour. So how do you select a treatment technology? And what I like to typically tell our customers is that try to come in with as open mind as you can. Don't say, I want to use a blow and ion or a blow and arc technology. Let's take a look at what material you're trying to treat. We have a bit of knowledge as far as, does this material treat better with this system or another system? The conductive or non-conductive piece comes into the equation like we talked about. The area to be treated, is it a small strip? Is it a large piece? That will impact as well. How is the part handled? Is it traveling down a conveyor? Is it in some sort of puck? Is it rotating on a table? Or is it some sort of robotic application? Those all come into play. Speed or cycle time that you're trying to achieve is also an important bit. I mentioned with our blow and arc, they tend to be a little bit slower. Our blow and ion and flame systems tend to be a bit faster, and in slow speed applications probably aren't the right choice. All of these we like to do before we take on any application is put them to the test in our lab. We offer free lab testing to determine which technology or technologies might be the best fit for you. So what we're seeing on this slide is a bit of a test that we had conducted with an adhesive company on a polyethylene substrate with UV cured adhesives. The far left bar shows the control sample, which was not treated, and the 2 on the right, one with blow and ion and one with flame, the strength of that bond was 3.5 times greater after plasma treatment. So the effect that you can have is pretty significant when you choose the right technology combined with the right adhesive and the right curing solution. So to summarize the technologies quickly, blow and arc systems are not good for conductive materials, but they're good at wide surfaces and require the longest amount of dwell time. Blow and ion systems can treat conductive and non-conductive materials. They can treat wide surfaces with automation or multiple heads, and they require a short amount of dwell time. Variable chemistry plasma are not able to treat conductive materials. They're good with wide surfaces and do tend to require a little bit longer dwell time. Flame plasma systems will treat both conductive and non-conductive materials. They're great for wide surfaces in that we're able to build a wide variety size of burners, and the amount of dwell time required by them is very short. So now I'd like to hand the reins over to Frank to talk about syringe and Precision Valve Adhesive Dispensing Options.
Thank you very much. We're going to go to the next slide. And I want to thank everyone for being here today. I was asked to come in and discuss our abilities on the dispensing side for UV adhesives, and they range quite widely across the spectrum, from very simple to very complex solutions. Typically, what we want to do to start the evaluation process is identify what the best process is from the beginning. Identify what the production requirements are, what type of consistency and quality requirements are being demanded of the application, typically what human resources are available, and then also the complexity of the task, as that may contribute to the complexity of the solution. Inevitably, when you talk about dispensing equipment, again, you can start with something that's very simple at a tabletop and a syringe, and work your way all the way up to a very customized piece of automation equipment. So evaluating the budget of what you expect to get out of a potential solution is always a consideration as well. These investments can obviously vary widely, from a tabletop solution for under $1,000 to over $50,000, and more obviously for a very custom solution. And sometimes these budgets can often be counter to what the actual requirement may be. So having some creativity in how we design a solution as a dispensing partner is always something that's vital as well. And then also evaluating what your current manufacturing requirements may be and how they may mesh with your long-term goals. A solution may be perfectly suitable for what you're doing today, but obviously not make any sense based on projections you may have in the next 6 months to a year or longer. So I frequently talk to people that are looking to have capacity, have capabilities that are well beyond what they'll need currently, more so for flexibility's sake than anything else. We can go ahead, Mark. Some of the things that are always to be considered when you're looking at designing a dispensing system is typically one of the first things we ask is how the material is going to be packaged. Can it be handled very easily? Syringes through drums and anything in between can all be accommodated very easily. But identifying what that packaging type is in conjunction with the specific chemistry itself will start to allow a dispensing company like PVA to start identifying the appropriate fluid delivery system to actually move the material to the dispensing apparatus. Again, this can be a factor when determining the amount of pressure required in large production equipment, and subsequently the complexity of whether we're talking about a syringe adapter and mount to a valve or large 55-gallon drum pump for that matter. And again, all can be accommodated. It's just a matter of communicating what options there are. And many times the end user may not know this, and that's not unusual, but that's something that can be worked around and addressed fairly readily when working with material partners. And again, most dispensing companies have those relationships to kind of create a triangle, and with the dispensing, with the chemical company and the end user, to determine the appropriate volume to be utilized for a particular application. Specifically talking about UV chemistries today, typically we use black opaque Teflon lines as a standard across the board, even for moisture sensitive materials, frankly, here at PVA, just to standardize on the tubing, so that even if you change over in the field, you have the flexibility that you're not going to have any issues with UV penetration into the fluid lines itself. Many new UV materials contain aggressive secondary moisture cure mechanisms that have greater performance in shadowed areas. This has always been a common issue in the past as far as access of UV light. And I know that's something Mike will touch base on a little bit later. But that secondary cure mechanism, whether it be chemical, moisture, or even heat introduction, has always improved over time. and are, again, being used more readily. This also has to be taken into account when designing the dispensing system to make sure, again, that it's moisture-free as well as UV light-free. High-pressure hoses, again, for higher viscosity materials when we're looking at pumping systems are always also tend to be opaque and avoid UV penetration into the fluid lines as well. So that's usually not an issue there. Typically, we're using stainless steel or plastic fittings in the dispensing system. Acrylic-based UV materials at times can react with steel or brass units. You know, those are considerations that should be taken when designing a UV dispensing process. And during that, you know, curing phase, any type of crystallization due to inappropriate fittings or fluid delivery components would obviously restrict the flow of the material and subsequently clog a valve or a dispensing system. We can go ahead, Mike. Or I'm sorry, Mark. Did we skip one there? There you go. Thank you. Again, another consideration when designing the equipment is evaluating what the shear sensitivity of the material is. High shear pumping systems, and again, we tend to get into this as you're looking at a higher degree of accuracy in your dispensing system. Oftentimes, gear pumps or other type of metering processes that can be utilized. Anything that's got a high shear sensitivity can, again, cause crystallization in the chemistry itself, so evaluating that in the design to avoid the seizure of those pumps is a critical aspect as well. Typically, peristaltic or diaphragm pumps are preferred when possible, as opposed to shearing UV materials. Also evaluating what the dispenser sprayer coverage area is. You know, evaluating, okay, now that we've got the material going to the appropriate valve to do the task, you know, what is the appropriate valve at that point to do the task in question? Are we doing a bead application, a spray application? And then also assuring that UV light can access the dispensed materials. In some applications, we do have end users that, you know, frankly, they don't, and they rely on the shadow, the secondary cure mechanism, and you know, in a shadowing effect to remedy that situation. Typically, with UV materials, we process a lot of coating materials here and adhesives. Many are highly solvent-based. UV materials don't tend to be, you know, in that category. So typically, you're exhausting more so for odor than anything else. And typically, in some sort of enclosed dispensing system, we're talking about around 300 CFM airflow. And we also want to stabilize the temperature of the material as well to eliminate any variability in viscosity. You know, so we try to keep that in the neighborhood of 15 to 30 C. Thanks, Mark. You can go ahead. Jumping on the material temperature sensitivity, again, typically most coating and adhesive dispensing manufacturers will work with a chemical company to evaluate what type of variation there is in viscosity versus the temperature of the material. Again, this can be stabilized, so if we find that the chemistry, in fact, is very reactive to changes in temperature, and these things can be, frankly, as silly as, you know, a tank sitting next to a heating duct or an open window that may affect the temperature of the material throughout the day, all things that I've seen over my years here. Those can be stabilized. So controlling the temperature of the material tank, the fluid lines, and the valve itself, again, are all options if we find that the material is very sensitive. This, again, comes into play more so in a time and pressure scenario. We're relying on consistency in the chemistry to create a consistent application, because there is no metering in the process at that point. So these are more so for our most simple dispensing designs. Again, you know, we can improve this by introducing some sort of diaphragm or gear pump system that will actually proportion the material regardless of small variations in viscosity. So again, this will go back to a design consideration more than anything else. We can go ahead, Mark. This little chart is, again, just a brief overview of the complexity that we're looking at. And again, typically we'll start from a very manual system to a very automated system, and somewhere along the line here, we can figure out, based on what the conceivable budget for something like this, what the volume requirements are for the application at hand, and what level of automation is required. Is typically something that we would again evaluate when determining the appropriate piece of equipment to address this. Again, you can start very manual with a handheld wand on a tabletop very inexpensively. Again, typically these are time and pressure solutions, so the consistency of the shot-to-shot repeatability is typically somewhere in the upwards of 10% range. Again, they can go lower, but that's probably on the high side. And then we can start to introduce various stages of automation, whether it be something that's semi-automated with a fixed valve position and controlling the position of the part itself, which would improve on relying on the operator to consistently move by hand for the dispensing position. So some sort of semi-automated solution, all the way to a fully automated unit that can then again, consistently place both the part and the valve in a reliable position. Those solutions, again, also open the door to a myriad of dispensing solutions within the robot, again, all the way from a time and pressure solution to a highly accurate metering system that can get sub 2% shot-to-shot accuracy. Okay, we can go ahead, Mark. Again, the manual adhesive dispenser is, again, typically a time and pressure process via syringe or a dispense wand. This can be done by hand, and it's typically done by hand. You can also add a timed controller that can allow shot size consistency, and these are very small boxes that look like about a book size that have some sort of digital timer, and that can be initiated either via a foot pedal or by a hand switch. All this will do is provide more shot-to-shot repeatability, but again, if there's some sort of motion required from the operator during that dispensing process, you're still relying on the operator then at that point to assure that the desired coverage area is completed. This is obviously the lowest cost equation as far as getting into the market of the dispensing. Again, the shot repeatability can be nearly 10%. So for highly accurate, repeatable processes, most of our customers would want some sort of automation. These tend to be more general dispensing applications because, again, you're operator dependent for both the volume and the position. And also, this offers the lowest percentage material utilization, again, just due to waste and inconsistency in the position of the part of the valve itself. Okay, Mark? A semi-automatic dispenser, as we discussed through the equipment matrix, can combine either a time and pressure solution or a metered solution with some sort of basic repeatable motion. So in this scenario, we can address one or both of the cons of a handheld dispensing application, and provide added accuracy either with the dispense shot position, the dispense shot repeatability in a metered solution, or both. Again, there's a higher level of initial investment to do this to get that type of consistency, but then again, the repeatability can vary by the solution. Again, if you're staying with simply a time and pressure method, turning the valve on and off as opposed to metering, again, you can go anywhere from up to 10% down to 5% or below. Again, the con here is you're still utilizing some sort of manual part handling. It's a trade-off between doing that and getting the added positional accuracy. And again, obviously, it's a slightly higher initial investment, but again, the trade-off here is repeatability within some piece of the process itself. Okay, we can go ahead, Mark. The higher level of automation is, again, taking the part itself and the valve and putting it in a robotic positioning system. Here you can utilize motion to create a highly repeatable, accurate position for the dispensing process. Again, regardless of the dispensing or the robot itself, the dispensing accuracy is always going to, again, fall back to the fluid delivery design. So again, as accurate as a robot can be, and these are typically plus or minus 1/1000th of an inch repeatability on each axis. The shot-to-shot accuracy, whether it be a potting application, bead application, are all going to fall back to the fluid delivery design. So again, a time and pressure method still not going to get you out of the 5 to 10% volumetric accuracy range, regardless if you add a repeatable robotic positioning system. To get those improvements, yet again, we need to look at adding some sort of metering device. The advantages here are that, again, these are typically used for high volume repeatable processes, so they can be conveyorized or not. Many of the units that we manufacture are in line for high volume production processes. You get much greater material utilization because of the positioning system, so your waste of material goes down significantly. Again, many fluid delivery options are available, again, all the way from time and pressure to metered solutions, but again, across a spectrum of upwards of 30 to 40 valves in a product line, all customized for a specific material that you're utilizing. And again, the disadvantage here would be that there's a higher initial investment. There are robots on the market today that can be small tabletop, benchtop solutions all the way through these inline solutions. So again, depending upon the level of automation, the level of consistency and reliability you're looking for, these can all, again, be addressed in some sort of automated fashion. We can go ahead. And again, just in summary, while production requirements, will often dictate the dispensing solution, probably very much like we discussed on the surface treatment side, I would say, we also like to see our customers come in with somewhat of an open mind, because very many times the solution is not so obvious. There's oftentimes multiple solutions to a dispensing problem or application, and qualifying the appropriate or best solution is really the only way to discover what's going to work best in production. Because conceivably, 2 or 3 dispensing valves, maybe a couple of different robotic cells could be utilized to do this, and just finding the best one is really where a service and sales engineer can help you determine that. But most applications do come with a general idea of whether there's some sort of demand for automation, and typically that allows us to focus on, okay, where's our starting point for this application, where do we want to go as far as designing a system, and then within each segment of solutions, again, there are various options that we can look at to meet your specific requirements. But the appropriate dispensing partner should be working with you to determine, not necessarily, this is my off-the-shelf solution. More so, this is, what's best suited to fit your application, not just now, but in the long run, to make the most efficient use of your production requirements. You can go ahead. And at this time, again, I thank you for your time. I'm going to hand this over to Mike Kay to close out on the UV curing side. And Mike, you can take the reins from there.
All right. Thanks very much, Frank. I'm going to talk to you for a little bit now about when to use UV lamp versus an LED curing solution. So 2 different technologies, both being used today in UV curing applications. Now, at Lumen Dynamics, we design, we manufacture, and we support our customers in both lamp and LED technologies. So I will try to give an unbiased opinion on where each one has its benefits, and also let you know some of the limitations of each technology. So if we can go on to the next slide. I think it's important, before we talk about the different light technologies, to give a quick overview on the way that the curing reaction takes place. And UV curing starts with the photoinitiator that's included in whether that's a UV curable adhesive, ink, or coating. And the curing reaction starts when you have sufficient light of the correct wavelength range that is absorbed by the photoinitiator. And that's an important point to note because every photoinitiator has a very specific spectral range where they'll absorb light and start that reaction. And so it becomes obviously critical that you match the spectral output of the light source that you're using with the absorption range of the photoinitiator. And then once you have the polymerization reaction started, you need to provide enough energy to get that reaction through to a point where you're considering your material to be fully cured. And while there's many different variables along the way that can affect the final cured properties of your material, today, for our purposes, we're going to look at those properties directly controlled by the light source. And that would include the dose, and so we'll look at the irradiance or the energy density provided by the light source multiplied by the time. And in applications where the parts are being held in place, you obviously have an exposure time that your parts are being subjected to. While in other applications where the parts may be moving on a conveyor, the exposure time is often controlled by the speed of that conveyor, and that's the way that you control the dose of energy that gets to the UV adhesive or coating. The other important part is the spectral content, so the wavelengths of light that are being shown down onto the material. It's very important that that be taken into consideration. And then the last thing we'll talk about is heat. Now, heat is really a byproduct of the reaction. So the polymerization reaction is exothermic. It does generate heat. But the light source used, the light technology used in the curing process can have significant effects on the amount of heat seen by the parts. And so if this is a consideration with your parts, and often is in many different curing applications where heat is trying to be avoided, then this could be one of the areas where it may determine what technology is best for you. So we'll go on to the next slide. So when we talked about, the first point, we talked about the dose or the irradiance level. This slide here shows a comparison on the output of lamp and LED systems. And here I'm comparing LED spot cure to a lamp spot cure. If we look at the typical maximum irradiance from an LED spot curing system, today, most LED systems can achieve up to about 10 watts per square centimeter, which is really more than enough irradiance for almost any curing application. One of the limitations, though, you'll see is that they're really limited to small spot sizes, and that's how we're able to achieve the high irradiance level, such as 10 watts per square centimeters, by using a lens to focus that energy into a very small spot. So when you look at the actual optical power coming from an LED spot source, it's only about 500 milliwatts of optical power. So it's really not that high power, but because we focus it, we can generate significant irradiance in a small spot size. Now, if you look at a lamp spot curing system, you can see that you've got significantly higher irradiance available, up to 30 watts per square centimeter, much higher than you would use for most curing applications. So most spot curing systems will give you the option of adjusting the amount of output down from 30 watts per square centimeter. You can see the spot size is also much larger than available with LED, and that's because when you look at the optical power, a typical lamp spot curing system has about 10 times the optical power than an LED system. And so you have the flexibility there of using larger spot sizes, going to multiple spots, and you have the potential of also curing faster because you can now have a higher amount of power available to you for the curing process. One of the ways we've looked at overcoming this with LEDs is by developing what we call LED area cure systems. And so these, again, you're able to get a nice irradiance level of 8 watts per square centimeter, which will be sufficient for most curing. But with the area curing, you're now covering a much larger area, about 25 by 50 millimeters, so 1 inch by 2 inch or 1 inch by 3 inch areas. So you're now talking hundreds of LEDs within that area. And now your optical power is now much, much higher. And that starts to give you much more flexibility in your curing. You're no longer limited to small spot sizes. And what you can see then is at the bottom, while for most spot curing applications, the parts are generally held in place while the parts are given an exposure for 1, 5, or 10 seconds. With an LED area curing system, you start to have the flexibility now of continuous curing. And so you can start to use conveyor type curing and continuously curing your parts and start to increase your throughput. And that's because of, again, there's a much higher optical power that's available to you for the curing. So that's the output power. If we move on to the next slide, I'm going to show you the differences in the spectral content between a lamp-based system and an LED. And this is really one of the key differences between lamp and LED technology. So what this chart shows here is the blue line is a typical mercury arc lamp. In this case, we've actually filtered the spectral output of the lamp. So this is using a 320 to 500 nanometer filter. The full spectrum of a mercury lamp will extend from 200 nanometers and below, where you start to actually generate ozone, which could be an issue for some applications. And it extends up well into the infrared, so well above 700, 800 nanometers, where you can start generating heat from that spectrum. And so the lamp is a very broad spectrum versus the 3 smaller peaks in the center is our LED spot curing spectrums. And you can see those 3, we have 3 different wavelengths available at 365 nanometers, 385 nanometers, and 400 nanometers. You're now looking at very narrow bandwidths, typically about 15 nanometer bandwidth. Lower power, but this narrow bandwidth means that the LEDs now, you need to be very specific on which wavelength you use, again, when we talk about matching that up to the photoinitiator. So if we go on to the next slide, you'll see that one of the key differences and things to keep in mind when looking at the different technology is the adhesive or the coating or ink compatibility. And so we talked about that you need sufficient light of the correct wavelength range to start the reaction. When you're using a lamp-based system where you have a very broad spectral output, it's much easier to match up the output of your light system to the requirements of the photoinitiator. When looking at an LED in those very narrow bandwidths, now it's very critical that you understand the absorption range of your photoinitiator, because you need to make sure that you match up the bandwidth of LEDs that you're using with the requirements of the photoinitiator. In some cases, this may limit your choice of adhesives. Depending on the photoinitiators being used, you may not be able to match up to the LEDs available. Typically, we see LEDs available of 365, 385, and 400 nanometers are very typical. There are LEDs available in higher wavelengths. But today, from a commercial availability, 365 nanometers is really as low a wavelength as is commercially available. So in this case, if adhesive compatibility is one of the key factors that you're looking at, and this could be, for example, if you use multiple adhesives with different photoinitiator absorption range, you're certainly going to have an easier time matching up those requirements using a lamp-based curing system. So if we move on to the next slide, on the flip side of that, the real benefit of the LED is that because you're using that very narrow spectrum of light, you are able to minimize the heat that is being generated during the curing process, because you're being very specific on the wavelengths of light to the requirements of the photoinitiator. Now, in a curing reaction, you have light that's being absorbed by the adhesive, but you also have light that can be absorbed by the parts. And things like dark or colored materials will often absorb visible light, and many plastics will absorb light below 300 nanometers, for example, depending on the plastic being used. So if you're introducing a broad spectrum of light, such as a lamp-based system, only a portion of that spectrum may be used by the adhesive, whereas a large portion of that may be absorbed by the parts, generating heat. Now, with the lamp systems, we do use things, bandpass filters. So we filter out some of the unwanted wavelengths of light in order to reduce the heat. But certainly the narrow spectrum of the LEDs ensures the lowest amount of heat. So for many different applications where the heat is critical, and I mentioned before on some of the applications like the OLED displays or touch panels, where it's really critical for their yields that they minimize the amount of heat. That's why some of these applications are now looking to transition to LED because they have the benefit of that narrow spectrum reduced heat during the curing process. On to the next slide, please. Now, one of the things to consider, though, again, with the curing process is the surface finish. And this is one of the areas comes up a lot when people are looking at using LED technology. And that is with a number of different adhesives, coatings, particularly with the free radical adhesives and coatings. They're susceptible to what's called oxygen inhibition. And what that is what, even though you may cure the formulation, you end up with a tacky surface. And there are ways that you can improve upon this situation. There's specific adhesive and coating formulations that are available to minimize the problem. And Frank talked about some of these with a secondary cure mechanism, such as a moisture cure. So you have different formulations available to improve this. But another way that is typically used to improve the surface finish on adhesives and coatings in particular is through the use of UVC, short wavelength UV. And you can see in the chart to the right, there's a blue highlight for the area of UVB and UVC wavelengths. Now, that's very typically used to improve the surface finish on the different UV curable formulations. Unfortunately, as I mentioned, with LEDs, and you can see the peak just to the right of that at 365 nanometers, that's as low as the LEDs go today. And so you don't have that short wavelength light available to improve the surface finish. So again, this is another area where it's key to keep in mind if surface finish is important in your application and the formulation you're using isn't compatible with the LED to produce a nice, hard, glossy finish, then this may be, again, a limitation of using LED, and lamp-based systems may be something for you to look at in this case. So moving on to the next slide. Certainly one of the areas where the LEDs do provide significant advantage, and one of the reasons that a lot of applications and a lot of customers, again, are looking at transitioning to LED is because of the lifetime. Typically, LEDs, you can get 20,000 hours plus of lifetime. And this really depends upon a couple of things on how hard you drive the LEDs and the temperature of the LED itself. It's key with your systems that you maintain a junction temperature that's within the specifications of the LED to get the lifetime. Now, Mark talked about one of the myths of the LEDs, and one of the things we hear quite often is the misconception that LEDs do not degrade over time. And what this chart shows is even though you will get very long lifetimes of the LED, they do degrade over time. And so again, that's another consideration within your process, is to set your LEDs at a level to minimize the degradation over time, but also to manage that and to be able to measure the output as your process goes to ensure that you're getting repeatable output. Now, if you look at a lamp-based system, these typically last 3,000 to 4,000 hours, so the 20,000 hours of an LED is definitely a significant advantage and can help in reducing the running costs for your process. And that's one of the reasons, again, we have people looking at LED as a technology for their curing process. So we'll go on to the next. And so along with lasting longer, certainly when you look at LEDs from an environmental perspective, they have certain advantages that people are looking at. And we have people looking at UV curing as a green technology because of the materials being used. The materials are very low in solvent content, so the VOC content is much lower than other solvent-based inks or coatings, for example. But the other thing with LEDs is that they require significantly less electrical power to run versus the comparable lamp system. And so again, we have a number of customers in applications such as the fiber coating, where the savings from electrical power on switching from a lamp to an LED is enough for them to look at making that transition, and the savings on running costs is enough for them to actually pay for the capital costs of the equipment. And so that's definitely a consideration for people when they're looking at whether LED or lamp is the best form of light technology for their application. And then we'll go on to the next one, Mark. So if we give a quick summary on what we advise our customers when they're looking to whether or not to use lamp or LED-based technology in their curing. Things we've talked about, the lamp has higher power. Certainly the adhesive compatibility of the broad spectrum is easier with the lamp versus the LED, where the narrow spectrum certainly helps you to minimize the heat. And so for heat-sensitive applications, LED has definite advantages. Also, things like the longer lifetime, the lower energy consumption can certainly provide some ongoing cost savings for your application by using LED. Lamp, things like surface finish may be a benefit there as well. And so what we've seen is lamp curing. It's an established technology. It's been done for many, many years versus LED, which is emerging. There's a lot of people who are interested. And what we recommend to anybody who is looking at potentially making the transition from a lamp to an LED-based curing technology is that they are very different light technologies. And so whenever you're looking at switching, you do need to take into account that with the different technologies, you will potentially get different properties from your adhesive, from your coating. So you need to look at developing a new process, and along with that, new testing parameters to ensure that the materials that you are coming with at the end of your curing process meet the requirements for your parts. And if you do that, then there may be some definite benefits when looking at LED curing technology. And with that, I'm going to turn it back over to Frank Hart, who's going to look at some different options for automating your process.
Thank you again, Mike. Just to close out, I know we're running up on time here, so I just want to briefly touch base. Really what we want to illustrate here is that automation companies are very frequently taking these somewhat related technologies and combining them into a complete solution. We've worked with surface treatment companies and integrated their products into our gantry systems to create more of a complete solution for our customers. This provides the ability to treat, dispense, and frankly cure, which we'll cover in a second, all in one operation, thus reducing the handling between operations. We can take the surface treatment units and software control the initiation of these units on and off. Again, provide full automation motion, and they can typically be integrated on any type of robotic system from a benchtop to a fully inline conveyorized system. Again, just to speed up the manufacturing process and reduce handling time. Next slide. Very similarly, UV cure integration is very common these days as well, and the LED and lamp guide integration can be done on a robotic cell to immediately cure to achieve favorable results. This can be done for a variety of ways. It's financially viable in many ways compared to a larger inline cure oven. Again, it does affect cycle times to a certain degree because there is a secondary step within the dispensing process. But it also can limit undesirable flow or uneven cured surfaces by controlling the amount of time from dispense to cure immediately within the dispensing process. Again, this is ideal for smaller coverage areas, dots, or beads, though frankly, companies like mine are always working with companies like or working with people like Mike at Lumen Dynamics as far as, what are they doing to push the envelope as far as opening up that window for us. We're always looking for new technologies to further those processes and capabilities for our customers. Again, this can eliminate the need for a full-sized inline oven, thus reducing floor space and obviously reducing significantly the initial capital investment for a solution. Very much like the surface treatment system, the UV LED systems can be software controlled on and off and are safe to be handled on a benchtop or conveyorized system as well. Again, identifying the material up front to determine the appropriate wavelength is a key element, and also determining how this is going to get mounted and where the power supply is going to be to determine that the light guide length is long enough for the application to cover the work area are both considerations that an engineering team would work with you as an end user to determine the appropriate models to use and part numbers to make sure that the task is satisfied appropriately. We're all set?
All right, let's mark again. We are at 1 hour, and we are going to open up to a few questions here in the final moments. Again, a quick review of some of the things we learned today. Surface treatment can improve bonding. It's very critical to define your application so that you know that you're getting the right equipment solutions with your vendors. And LED curing is certainly a highly effective alternative to UV lamps, but again, depending upon your specific application requirements. So again, I'd like to thank Mike, Frank, and Ryan for their presentations today, as well as our audience's time and interest in today's topics. So let's take a look at some of the questions. I have one here for Mike. Mike, the question is, the person's interested in changing from a lamp curing system to an LED. What is the process they would need to take to make this transition?
Thanks, Mark. I mean, that is something we work with quite a bit on with our customers today. And so one of certainly the things we look at when making that transition is, one, we need to identify whether or not the adhesive or the ink or coating that they're using is compatible with the LED technology, and that's the first thing that we do. And we can actually provide some testing here to help the customer make that determination. The next thing we need to look at is whether or not the LED has enough energy to cure that in the time requirements that they have. And so certainly most production requirements, there's a specific amount of time allocated for the cure, and we need to make sure the LED can perform the curing within that time. And then just as importantly, we identify the testing that will go into qualifying what is a successful cure. And that can be, in the case where you're bonding two parts together, a pull test. In case of printing, it could be things like a scratch test. Because again, the physical properties of the cured parts may be different based on whether or not it's cured with a lamp versus an LED system. And finally, we need to look at the measurement tools of the output. So we talked about the fact that lamps and LEDs will both degrade over time. And so the measurement tool, the radiometer being used for the lamp, will not be appropriate for using the LED. So we have to make sure that they're using the appropriate tools to measure that output. And so once that's all in place, then we're able to look and see whether or not the transition makes sense. Sometimes it does. Sometimes customers have the flexibility to look at different formulations that may be better suited to LED, and this certainly helps with the process. But other times they don't want to change the formulation, and then in those cases, LED may not be suitable.
Thanks, Mike. I've got a question here for Ryan. This person wants to know what are some of the ways that they can determine which surface treating technology would be best to improve their processes.
It's a great question, and one that we get quite often. We've got a number of steps that we'll take in evaluating a process for a potential customer. And the first step that we'll typically take is we'll utilize our in-house lab, which is pretty unique in the fact that we have 3 or 4 different plasma treating technologies, the blow-in arc, blow-in ion, variable chemistry, and flame plasma systems. We're able to take those, run and simulate your production environment, test them, see what the difference. Usually we'll measure it based in dyne levels and see what the dyne increase is. Typically that gives us an idea whether your end success will be successful or not. We then take those parts. They're typically next day aired back to you to run whatever your process might be. We'll then take it from there, and we can do everything from, we have manufacturers reps located not only around the country but around the world who have these systems and can then pay a visit, install a system in your facility, and test it out as well.
Thanks, Ryan. Frank, this is a question for you. For very small adhesive drops, could you comment on how to select the dispensive needle to reduce surface tension on the needle to help the tiny drop detach from the needle? Would a coated needle help? What about the shape of the needle, conical versus straight?
Yeah, sure. Thanks, Mark. Yeah, we're seeing, particularly in the micro dispensing realm, we're seeing needles become a greater factor, actually. Coated needles, we're seeing ceramic needles. There's a variety of tips available on the market now. Again, some of this will be determined by the desired shot size itself and the chemistry. We would also look at whether there's any filler in the chemistry itself that may clog such a small needle. So again, if we're looking at a fairly low viscosity or friendly adhesive, there's a lot of options available for reducing back pressure. I would say more of what we call a free flow tip, or it would be more of a slight taper tip. It would probably be the more common use. And again, for the micro dispensing portion of that question, I would look at something that was probably more machined. The free flow tips are available in plastic reusable designs, but I'd probably look at these as more of a metal or a ceramic chemistry or material that we would use for that portion.
All right, Mike, question. Could you comment on cure homogeneity difference with LED or HG arc spot cure systems?
Yeah, and that's a good question. With the spot, you do tend to get a more homogeneous spot with the lamp-based system, because what happens is the light is being directed through a light guide with the lamp-based system, and you get a bit of mixing within that guide, and so you tend to get a more uniform spot versus an LED. With an LED, we have specific lenses that we use, and so what you need to do when setting up your LED process is you need to make sure you have the correct lens for both the working distance and the spot size that you require. Because what will happen is, because the LED light is very focused, if you don't have the correct lens for both the working distance and the spot size, you can end up with a higher radiance in the center with a drop-off around the edges. With the lamp systems and the light guides being used, it tends to be a little bit more flexible in the working distances that you're able to do and still maintain a very homogeneous spot.
Thanks, Mike. We've certainly gone over time here, and in respect to everyone, we will conclude the webinar now. However, if we did not get a chance to answer your question, we will be sharing these with the panelists, and they will follow up with you. We'd like to thank you again for your time today. Everyone attending today will receive an email with access to the recording of the webinar and the presentation slides once they are posted online, which should be in a day or two. Thank you again, and this concludes today's webinar.